a modelled image in a moment similar to that. So just to sort of keep that in the back of your mind about how we can actually view things at an oblique angle. A few years ago, this is the southern part of the Loddon catchment, and Ballarat sits in about this location here, Bendigo in about this location over here. A few years ago, using the bore logs, we modelled up the thickness of the deep lead, or the basal gravel aquifer, which is buried below basalts in this area. And the colours in this, particularly the greens, blues, and the white point, are the thickening portions of the deep lead. Ignore the oranges and yellows; they basically represent zero thickness, and they're actually on the sides and the flanks and the hilltops where there was no deposition. We have some sort of rudimentary paleo river trace running through there, just a line trying to join the deepest points and the thickest parts of the valley. So let's view that obliquely. So I hope you can see there the shape of the valley, similar to that Google image I showed a while ago. The valley floor, valley sides. These are paleo hills, if you would say, or paleo topography. And representing this is the thickness of that basal aquifer. Now, in 2006, Holgate and some co-authors interpreted a number of northeast trending fault structures based on the shuttle terrain model, and these ran through our area. This portion of the image here is the Loddon River, and a number of these fault lines ran through this area. And when we placed that on top of our data, we found an interesting situation where we've got these thick patches of deep lead adjacent to the faults. So the interpretation there is that the faulting that they've interpreted in a separate study was contemporaneous with the formation of that deep lead. As the river was flowing and depositing gravels and sands, we've got some faulting that's going on, and it's deepening the basin, and we can actually see that effect here, with particularly this one here and this one here, that even though the river continued through there, the deposition is actually occurring upstream and downstream of these two faults. This is another view of the Loddon catchment. This one's from the northwest, looking back towards Melbourne. It's the modelled paleo topography of that area, the upper part of the catchment. We can pick up drainage lines coming through in different places. This smooth area in here is the forced data based upon the forced modelling, I should say, based on the borehole data. There's an anomaly turned up in this area here where there's a 50-metre cliff modelled there. That's simply because there's a number of boreholes included that were excluded from the data in this area, and it's just created a cliff. So please ignore that one. That's an anomaly. If you remember a while ago, I mentioned the voxels are like little Lego cubes. When we model up using GoCAD, we can actually get a volume calculation for the deep lead, and the green in this image is that deep lead as it's been modelled, and we can see and calculate a volume for the deep lead gravels and our aquifer. And if we know the porosity, then we're able to actually calculate a potential volume of water in that aquifer. The next layer of that's actually the basalts. Now these basalts are 60 to 80 metres thick, and they've covered up that basal gravel. That's the definition for deep lead in Victoria is that it's an ancestral river gravel that's buried under basalt, and in this particular case case, this is the Malort volcanic field between Creswick and Ballarat. And where's my mouse gone? A number of these shapes here are actually volcanic cones, and the blocky nature of that is due to those voxel modelling that I was mentioning a while ago. And this is the shuttle terrain model as based from, as derived from the shuttle data for that same area. You can see it's actually been enhanced vertically by about 10 times just to show up things like these volcanic cones in the terrain, and the smoother country that runs from about this location across to about here. That's the basalt fill in the valley, and all of this sort of speckly, complex country in here is not covered by basalt. And this line running through here is the Long River. So concluding parts to that, we've had some early successes with identifying errors. We're starting to understand aquifer geometry, and what we're interpreting is actually aligning with other people's studies. That is that fault model which was described earlier. 3D modelling, it's an essential part to try and understand what we've got subsurface in these aquifers. Really try and build the picture just from 2D or 1D models is going to introduce a whole heap of difficulties and misunderstandings, and this way with 3D models we can actually present that model to managers and they can get a better understanding of what we're seeing. And a lot of this is, does it actually fit what we understand? Some of those anomalies don't look right. That's how we pick them. So the visual checking is a really powerful tool. There's things that you won't pick up by looking through a table or a list of numbers, but it's only when you start visualising it that you actually get to see the differences and the errors. And the last point there, the last line, is how many times have you walked into a room and felt the need to straighten a picture that's hanging on the wall that's only out by 1 or 2 millimetres? The power of your eye to pick up anomalies is really strong. And thank you. There's just some extra reading if you're interested.